Hi there, this is Soman and you're watching the Genesis YouTube channel. I invite you to come along a series of voyages to explore the universe as astronomers understand it today. Beyond Earth, there are vast and magnificent realms full of objects that have no counterpart on our home planet. Nevertheless, I hope to show you that the evolution of the universe has been directly responsible for your presence on Earth today. Along your journey, you will encounter a canyon system so large that on Earth it will stretch from Los Angeles to Washington DC. A crater and other evidence on Earth that tells us that dinosaurs and many other creatures died because of a cosmic collision. A tiny moon whose gravity is so weak that one good throw from its surface could put a baseball into orbit. A collapsed star so dense that to duplicate its interior we would have to squeeze every human being on the Earth to a single raindrop. Exploding stars whose violent end could wipe clean all of the life forms on a planet orbiting a neighboring star. A cannibal galaxy that has already consumed a number of its smaller galaxy neighbors and is not yet finished finding new victims. A radio echo that is the faint but unmistakable signal of the creation event for our universe. Such discoveries are what make astronomy such an exciting field for scientists and many others. But you will explore much more than just the objects in our universe and the latest discoveries about them. We will pay equal attention to the processes by which we have come to understand the realms beyond Earth and the tools we use to increase that understanding. We gather information about the cosmos from the messages the universe sends our way. Because the stars are the fundamental building blocks of the universe, decoding the messages of starlight has been a central challenge and triumph of modern astronomy. By the time you have finished with this video series, you will know a bit about how to read that message and how to understand what it is telling us. Astronomy is defined as the study of the objects that lie beyond our planet Earth and the processes by which these objects interact with one another. It is also humanity's attempt to organize what we learn into a clear history of the universe, from the instant of its birth in the Big Bang to the present moment. Throughout this series, I will emphasize that science is a progress report, one that changes constantly as new techniques and instruments allow us to probe the universe more deeply. In considering the history of the universe, we will see again and again that the cosmos evolves. It changes in profound ways over long periods of time. For example, the universe made the carbon, the calcium, and the oxygen necessary to construct something as interesting and as complicated as you. Today, many billions of years later, the universe has evolved into a more hospitable place for life. Tracing the evolutionary processes that continue to shape the universe is one of the most important and satisfying parts of modern astronomy. The ultimate judge in science is always what nature itself reveals based on observation, experiments, models, and testing. Science is not merely a body of knowledge but a method by which we attempt to understand nature and how it behaves. This method begins with many observations over a period of time. From the trends found through observations, scientists can model the particular phenomenon which we want to understand. Such models are always approximations of nature, subject to further testing. As a concrete astronomical example, ancient astronomers constructed a model, partly from observations and partly from philosophical beliefs, that Earth was the center of the universe and everything moved around it in circular orbits. At first, our available observations of the Sun, Moon, and the planets did fit this model. However, after further observations, the model had to be updated by adding circle after circle to represent the movements of the planets around Earth at the center. As centuries passed and improved instruments were developed for keeping track of objects in the sky, the old model, even with the huge number of circles, could no longer explain all the observed facts. As we will see later, that a new model with the Sun at the center fit the experimental evidence better. After a period of philosophical struggle, it became accepted as our view of the universe. When they are first proposed, new models or ideas are sometimes called hypotheses. You may think there can be no new hypothesis in a science such as astronomy, that everything important has already been learned. Nothing could be further from the truth. Throughout this series, you will find discussions of recent and occasionally still controversial hypotheses in astronomy. For example, the significance that the huge chunks of rock and ice that hit Earth have for life on Earth itself is still debated. And while the evidence is strong that vast quantities of invisible dark energy make up the bulk of the universe, scientists have no convincing explanation for what the dark energy actually is. Resolving these issues would require difficult observations done at the forefront of our technology, and all such hypotheses need further testing before we incorporate them fully into our standard astronomical models. This last point is crucial. A hypothesis must be a proposed explanation that can be tested. The most straightforward approach to such testing in science is to perform an experiment. If the experiment is conducted properly, its result will either agree with the predictions of the hypothesis or they will contradict it. If the experimental result is truly inconsistent with the hypothesis, a scientist must discard the hypothesis and try to develop an alternate. If the experimental result agrees with predictions, this does not necessarily prove that the hypothesis is absolutely correct. Perhaps later experiments will contradict crucial parts of the hypothesis. But the more experiments that agree with the hypothesis, the more likely we are to accept the hypothesis as a useful description of nature. One way to think about this is to consider a scientist who was born and lives on an island where only black sheep live. Day after day, the scientist encounters black sheep only. So he or she hypothesizes that all sheep are black. Although every observed sheep adds confidence to the theory, the scientist only has to visit the mainland and observe one white sheep to prove the hypothesis is wrong. When you read about experiments, you probably have a mental picture of a scientist in a laboratory conducting tests or taking careful measurements. This is certainly the case for a biologist or a chemist. But what can astronomers do when our laboratory is the universe? It is impossible to put a group of stars into a test tube or order another comet from a scientific supply company. As a result, astronomy is sometimes called an observational science. We often make our tests by observing many samples of the kind of object that we want to study and noting carefully how different samples vary. Much of astronomy is also a historical science, meaning what we observe has already happened in the universe and we can do nothing to change it. While this can make astronomy challenging, it also gives us fascinating opportunities to discover the secrets of our cosmic past. You might compare an astronomer to a detective trying to solve a crime that occurred before the detective arrived at the scene. There is lots of evidence, but both the detective and the scientist must sift through and organize the evidence to test various hypotheses about what actually happened. And there is another way in which the scientist is like a detective. In both cases, one can only ask for evidence beyond a reasonable doubt. And sometimes, new evidence will force both the detective and the scientist to revise their last hypothesis. This self-correcting aspect of science sets it off from most human activities. Scientists spend a great deal of time questioning or challenging one another, which is why applications for project funding, as well as reports for publication in academic journals, go through an extensive process of peer review, which is a careful examination by other scientists in the same field. In science, after a formal education and training, everyone is encouraged to improve upon experiments and to challenge any and all hypotheses. This is one of the reasons science has made such dramatic progress. An undergraduate science major today knows more about science and math than did Sir Isaac Newton, one of the most renowned scientists who ever lived. Even in this introductory astronomy series, you will learn about objects and processes that no one a few generations ago even dreamed existed. Over centuries, scientists have extracted various scientific laws from countless observation, hypotheses, and experiments. These scientific laws are, in a sense, the rules of the game that nature plays. One remarkable discovery about nature, one that underlies everything we will see in this series, is that the same laws apply everywhere in the universe. The rules that determine the motion of stars so far away that your eye cannot see them are the same laws that determine the arc of a cricket ball after a batsman has hit it outside the stadium. The consistency of laws of nature gives us enormous power to understand distant objects without traveling to them and learning the local laws. This is not to say that our current scientific models and laws cannot change. New experiments and observations can lead to new, more sophisticated models that can include new phenomena and laws about their behavior. The general theory of relativity proposed by Albert Einstein is a perfect example of such a transformation that took place about a century ago. It led us to predict and eventually to observe a strange new class of objects that astronomers called black holes. Only the patient process of observing nature ever more carefully and precisely can demonstrate the validity of such new scientific models. One important problem in describing scientific models has to do with the limitations of language. When we try to describe complex phenomena in everyday terms, the words themselves may not be adequate to do the job. For example, you might have heard the structure of the atom likened to a miniature solar system. While some aspects of our modern model of atom do remind us of planetary orbits, many other of its aspects are fundamentally different. This problem is the reason scientists often prefer to describe their models using equations rather than words. In this video series, which is designed to introduce the field of astronomy, I will use mainly words to discuss what scientists have learned. I will avoid complex math, but if this series piques your interest and you go into science, more and more of your studies will involve the precise language of mathematics. In astronomy, we deal with distances on a scale you may never have thought of before, with numbers larger than any you might have encountered. We adopt two approaches that make dealing with astronomical numbers a little easier. First, we use a system for writing large and small numbers called scientific notations, or sometimes powers of 10 notation. This system is very appealing because it eliminates the many zeros that can seem overwhelming to the reader. In scientific notation, if you want to write a number such as 500, 1000, you express it as 5 into 10 power 8. The second way we try to keep numbers simple is to use a consistent set of units. The Metric International System of Units, or SI. A common unit astronomers use to describe distances in the universe is a light year, which is the distance light travels during 1 year. Because light always travels at the same speed, and because its speed turns out to be the fastest possible in the universe, it makes a good standard for keeping track of distances. So, how many kilometers are there to a light year? Light travels at the amazing pace of 3 into 10 power 5 kilometers per second, which makes a light year 9.46 into 10 power 12 kilometers. You might think that such a large unit would reach the nearest star easily, but the stars are far more remote than our imaginations lead us to believe. Even the nearest star is 4.3 light years away, more than 40 trillion kilometers. Other stars visible to the unaided eye are hundreds to thousands of light years away. This beautiful cloud of cosmic raw material, gas and dust from which new stars and planets are being made is called the Orion Nebula, and this is about 1400 light years away. That's a distance of roughly 1.34 into 10 power 16 kilometers, a pretty big number. There is another reason the speed of light is such a natural unit of distance for astronomers. Information about the universe comes to us almost exclusively through various forms of light, and all such light travels at the speed of light, that is, 1 light year every year. This sets a limit on how quickly we can learn about the events in the universe. If a star is 100 light years away, the light we see from it tonight left that star 100 years ago and is just now arriving at our neighborhood. The soonest we can learn about any changes in that star is 100 years after the fact. For a star 500 light years away, the light we detect tonight left 500 years ago and is carrying 500-year-old news. You might ask that when I see that star up there, I won't know what's actually happening there for another 500 years. Yes, but this isn't the most helpful way to think about the situation. For astronomers, now is when the light reaches us here on Earth. There is no way for us to know anything about the star or any other object until its light reaches us. What may at first seem a great frustration is actually a tremendous benefit in disguise. If astronomers really want to piece together what happened in the universe since its beginning, they must find evidence about each epoch or period of time of the past. where can we find evidence today about cosmic events that occurred billions of years ago? The delay in the arrival of light provides an answer to this question. The farther out in space we look, the longer the light has taken to get here, and the longer ago it left its place of origin. By looking billions of light years out into space, astronomers are actually seeing billions of years into the past. This way, we can reconstruct the history of the cosmos and get a sense of how it has evolved over time. This is one reason why astronomers strive to build telescopes that can collect more and more of the faint light in the universe. The more light we collect, the fainter the objects that we can observe. On an average, fainter objects are farther away and can therefore tell us about periods of time even deeper in the past. Instruments such as the Hubble telescope or the Very Large Telescope in Chile are giving astronomers view of deep space and deep time better than any we have done before. We can now take a brief introductory tour of the universe as astronomers understand it today, to get acquainted with the various types of objects and distances we will encounter through this series. We begin at home with Earth, a nearly spherical planet about 13,000 kilometers in diameter. A space traveler entering our planetary system would easily distinguish Earth from the other planets in our solar system by the large amount of liquid water that covers some 2/3 of its crust. Our nearest astronomical neighbor is Earth's satellite, commonly called the Moon. This figure shows Earth and Moon drawn to scale on the same diagram. The Moon's distance from Earth is about 30 times Earth's diameter, or approximately 384,000 kilometers. And it takes about a month for the Moon to revolve around Earth. The Moon's diameter is 3,476 kilometers, about 1/4 the size of Earth. Light or radio waves takes 1.3 seconds to travel between Earth and Moon. If you have seen videos of the Apollo flights to the Moon, you may recall that there was a delay of about 3 seconds between the time Mission Control asked a question and the time astronauts responded.
Hey, this is Houston, loud and clear. Break, Buzz, this is Houston. Radio check and verify TV circuit breaker in. Roger, TV circuit breaker's in.
This was not because the astronauts were thinking slowly, but rather because it took the radio waves almost 3 seconds to make the round trip. Earth revolves around our star, the Sun, which is about 150 million kilometers away, approximately 400 times as far away from us as the Moon. We call the average Earth-Sun distance an astronomical unit because in the early days of astronomy, it was the most important measuring standard. Light takes slightly more than 8 minutes to travel 1 astronomical unit, which means that the latest news we receive from the Sun is always 8 minutes old. The diameter of the Sun is about 1.5 million kilometers. Earth could fit comfortably inside one of the minor eruptions that occurs on the surface of our star. If the Sun were reduced to the size of a basketball, Earth would be a small apple seed about 30 meters from the ball. It takes Earth 1 year, or 3 into 10 past 7 seconds, to go around the Sun at our distance. To make it around, we must travel at approximately 110,000 kilometers per hour. Because gravity holds us firmly to Earth and there is no resistance to Earth's motion in the vacuum of space, we participate in this extremely fast-moving trip without being aware of it day to day. Earth is only one of the 8 planets that revolve around the Sun. These planets, along with their moons and the swarms of smaller bodies such as dwarf planets, make up the solar system. A planet is defined as a body of significant size that orbits a star and does not produce its own light. If a large body consistently produces its own light, it is then called a star. Later in this series, we will modify this definition of a planet, but it is perfectly fine for you as you start your journey. We are able to see the nearby planets in our skies only because they reflect the light of our local star, the Sun. If the planets were much farther away, the tiny amount of light they would reflect would usually not be visible to us. The planets we have so far discovered orbiting other stars were found from the pull their gravity exerts on their parent stars, or from the light they block from the stars when they pass in front of them. We can't see most of these planets directly, although a few are now being imaged directly. The Sun is our local star, and all the other stars are also enormous balls of glowing gas that generate vast amounts of energy by nuclear reactions deep within. We will discuss the processes that cause stars to shine in more detail later. The other stars look faint only because they are so very far away. If we continue our basketball analogy, Proxima Centauri, the nearest star beyond the Sun, which is 4.3 light years away, would be almost 7,000 kilometers from the basketball. When you look up at a star-filled sky on a clear night, all the stars visible to the unaided eye are part of a single collection of stars we call the Milky Way galaxy, or simply the galaxy. Its extent, as we will see, staggers the human imagination. Within a sphere 10 light years in radius centered on the Sun, we roughly find 10 stars. Within a sphere 100 light years in radius, there are roughly 10,000 stars. Far too many to count or name, but we have still traversed only a tiny part of the Milky Way galaxy. Within a 1,000 light year sphere, we find some 10 million stars. And within a sphere of 100,000 light years, we finally encompass the entire Milky Way galaxy. Our galaxy looks like a giant disk with a small ball in the middle. If we could move outside our galaxy and look down at the disk of the Milky Way from above, it would probably resemble this figure, with its spiral structure outlined by the blue light from adolescent stars. This picture shows a galaxy of billions of stars called by its catalog name NGC 1073, and this is thought to be similar to our own Milky Way galaxy. Here we can see the giant wheel-shaped system with a bar of stars across its middle. The Sun is somewhat less than 30,000 light years from the center of the galaxy, in a location with nothing much to distinguish it. From our position inside the Milky Way galaxy, we cannot see through its far rim, at least not with ordinary light, because the space between the stars is not completely empty. It contains a sparse distribution of gas, mostly the simplest element hydrogen, intermixed with tiny solid particles that we call interstellar dust. This gas and dust collect into enormous clouds in many places in the galaxy, becoming the raw material for future generations of stars. This figure shows an image of the disk of the galaxy as seen from our vantage point. Typically, the interstellar material is so extremely sparse that the space between stars is a much better vacuum than anything we can produce in terrestrial laboratories. Yet, the dust in space, building up over thousands of light years, can block the light of more distant stars. Like the distant buildings that disappear from our view on a smoggy day, the more distant regions of Milky Way cannot be seen behind the layers of interstellar smog. Luckily, astronomers have found that stars and raw materials shine with various forms of light, some of which do penetrate the smog, and so we have been able to develop a pretty good map of the galaxy. Recent observations, however, have also revealed a rather surprising and disturbing fact. There appears to be much more to the galaxy than meets the eye or the telescope. From various investigations, we have evidence that much of our galaxy is made up of material we cannot currently observe directly with our instruments. We therefore call this component of the galaxy dark matter. We know the dark matter is there by the pull its gravity exerts on the stars and raw materials that we can observe. But what this dark matter is made of and how much of it exists remains a mystery. Furthermore, this dark matter is not confined to our galaxy. It appears to be an important part of other star groupings as well. By the way, not all stars live by themselves as the Sun does. Many are born in double or triple systems with 2, 3 or more stars revolving around each other. Because the stars influence each other in such close systems, multiple stars allow us to measure characteristics that we cannot discern from observing single stars. In a number of places, enough stars have formed together that we recognize them as star clusters. This large star cluster is known by its catalog number M9. It contains some 250,000 stars and is seen more clearly from space using Hubble telescope. It is located roughly 25,000 light years away. Some of the largest of the star clusters that astronomers have catalogued contain hundreds and thousands of stars. You may hear stars referred to as eternal, but in fact no star can last forever. Since the business of stars is making energy and energy production requires some sort of fuel to be used up, eventually all stars run out of fuel. This news should not cause you to panic though, because our sun still has at least 5 or 6 billion years to go. Ultimately, the sun and all stars will die, and it is in their death throes that some of the most intriguing and important processes of the universe are revealed. For example, we now know that many of the atoms in our bodies were once inside stars. These stars exploded at the end of their lives, recycling their material back to the reservoir of the galaxy. In this sense, all of us are literally made of recycled stardust. In a very rough sense, you could think of the solar system as your house or apartment and the galaxy as your town made up of many houses and buildings. In the 20th century, astronomers were able to show that just as our world is made up of many towns, so the universe is made up of enormous number of galaxies. We define the universe to be everything that exists and is accessible to our observations. Galaxies stretch as far into space as our telescopes can see, many billions of them within the reach of modern instruments. When they were first discovered, some astronomers called galaxies island universes, and the term is aptly descriptive. Galaxies do look like islands of stars in the vast dark seas of intergalactic space. The nearest galaxy, discovered in 1993, is a small one that lies 75,000 light years from the Sun in the direction of the constellation Sagittarius, where the smog in our own galaxy makes it especially difficult to discern. A constellation, we should note, is one of the 88 sections into which astronomers divide the sky, each named after a prominent star pattern within it. Beyond this Sagittarius dwarf galaxy lie two other small galaxies about 160,000 light years away. First recorded by Magellan's crew as he sailed around the world, these are called the Magellanic Clouds. This image shows both the large Magellanic Cloud and the small Magellanic Cloud. All three of these small galaxies are satellites of the Milky Way galaxy, interacting with it through the force of gravity. Ultimately, all three may even be swallowed by our much larger galaxy, as other small galaxies have been over the course of cosmic time. The nearest large galaxy is a spiral quite similar to our own, located in the constellation Andromeda, and is thus called the Andromeda Galaxy. It is also known by one of its catalog numbers, M31. M31 is little more than 2 million light years away, and along with the Milky Way is a part of small cluster of more than 50 galaxies referred to as the local group. At distances of 10 to 15 million light years, we find other small galaxy groups, and then about 50 million light years there are more impressive systems with thousands of member galaxies. We have discovered that galaxies occur mostly in clusters, both large and small. In this image, you can see part of a cluster of galaxies located about 60 million light years away in the constellation of Fornax. All objects that are not pinpoints of light in the picture are galaxies of billions of stars. Some of the clusters themselves form into larger groups called superclusters. The local group is part of a supercluster of galaxies called the Virgo supercluster, which stretches over a diameter of 100 million light years. We are just beginning to explore the structure of the universe at these enormous scales and are already encountering some unexpected findings. At even greater distances, where many ordinary galaxies are too dim to see, we find quasars. These are brilliant centers of galaxies glowing with the light of extraordinary energetic processes. The enormous light of the quasars is produced by gas that is heated to a temperature of millions of degrees as it falls towards a massive black hole and swirls around it. The brilliance of quasars makes them the most distant beacons that we can see in the dark oceans of space. They allow us to probe the universe 10 billion light years away or more, thus 10 billion years or more in the past. With quasars, we can see way back close to the Big Bang explosion that marks the beginning of time. Beyond the quasars and the most distant visible galaxies, we have detected the feeble glow of the explosion itself, filling the universe and thus coming to us from all directions in space. The discovery of this afterglow of creation is considered to be one of the most significant events in 20th century science. And we are still exploring the many things that it has to tell us about the earliest times of the universe. The previous discussion has likely impressed on you that the universe is extraordinarily large and extraordinarily empty. On an average, it is 10,000 times more empty than our galaxy. Yet, as we have seen, even the galaxy is mostly empty space. The air we breathe has about 10 power 19 atoms in each cubic centimeter, and we usually think of air as empty space. In the interstellar gas of the galaxy, there is about 1 atom in every cubic centimeter. Intergalactic space is filled so sparsely that to find 1 atom, on an average, we must search through a cubic meter of space. Most of the universe is fantastically empty. Places that are dense, such as the human body, are tremendously rare. Even our most familiar solids are mostly space. If we could take apart such a solid piece by piece, we would eventually reach the tiny molecules from which it is formed. Molecules are the smallest particles into which any matter can be divided while still retaining its chemical properties. A molecule of water, H2O for example, consists of 2 hydrogen atoms and 1 oxygen atom bonded together. Molecules in turn are built of atoms, which are the smallest particles of an element that can still be identified as that element. For example, an atom of gold is the smallest possible piece of gold. Nearly 100 different kinds of atoms or elements exist in nature. Most of them are rare, and only a handful of them account for more than 99% of everything with which we come into contact. The most abundant element in the cosmos today are listed in this table. Think of this table as the greatest hits of the universe when it comes to elements. All atoms consist of a central positively charged nucleus surrounded by negatively charged electrons. The bulk of the matter in each atom is found in the nucleus, which consists of positive protons and electrically neutral neutrons, all bound tightly together into a very small space. Each element is identified by the number of protons in its atoms. Thus, any atoms with 6 protons in its nucleus is called carbon. Any with 50 is called tin. The distance from an atomic nucleus to its electrons is typically 100,000 times the size of nucleus itself. This is why we say that even solid matter is mostly empty space. The typical atom is far emptier than the solar system out to Neptune. This is one of the reasons why atoms are not like miniature solar systems. Remarkably, physicists have discovered that everything that happens in the universe, from the smallest atomic nucleus to the largest supercluster of galaxies, can be explained through the action of only 4 forces: gravity, electromagnetism, which combines the actions of electricity and magnetism, and 2 forces that act at the nuclear level. The fact that there are 4 forces and not a million or just one has puzzled physicists and astronomers for many years and has led to a quest for a unified picture of nature. If you are new to astronomy, you have probably reached the end of our brief tour with mixed emotions. On the one hand, you may be fascinated by some of the new ideas you have read about and you may be eager to learn more. On the other hand, you may be feeling a bit overwhelmed at the number of topics we have covered and the number of new words and ideas we have introduced. Learning astronomy is a little like learning a new language. At first it seems there are so many new expressions that you will never master them at all. But with practice, you will soon develop facility with them. At this point, you may also feel a bit small and insignificant, dwarfed by the cosmic scales of distance and time. But there is another way to look at what you have learned from our first glimpses of the cosmos. Let us consider the history of the universe from Big Bang to today and compress it for easy reference into a single year. This idea is borrowed from Carl Sagan's 1997 book, The Dragons of Eden. On the scale of a year, the Big Bang happened at the first moment of January 1. And this very moment when you are watching this video, would be the very last second of December 31st. When did other events in the development of the universe happen in this cosmic year? Our solar system formed around September 10th. and the oldest rock that we can date on Earth go back to the 3rd week in September. Where does the origin of human beings fall during the course of this cosmic year? The answer turns out to be the evening of December 31st. The invention of the alphabet doesn't occur until the 50th second of 11:59 p.m. on December 31st. And the beginnings of modern astronomy are a mere fraction of a second before the new year. Seen in a cosmic context, the amount of time we have had to study the stars is minute, and our success in piecing together as much of the story as we have is truly remarkable. Certainly, our attempts to understand the universe are not complete. As new technologies and new ideas allow us to gather more and better data about the cosmos, our present picture of astronomy will very likely undergo many changes. Still, as you watch through this series as a current progress report on the exploration of the universe, take a few minutes every once in a while just to savor how much you have already learned. This brings us to the end of this video. In the next video, we will learn about observing the sky and understand how the modern field of astronomy was born. There are many good resources, books, websites, videos which you can use, and I have listed them in the description below. The list is too long and therefore I won't waste any time in recounting them. Finally, if you like the work, like, subscribe and share widely amongst your friends. Till the next video, stay safe and stay healthy you all.